during this pandemic, there are a lot of things that we can do over Zoom meeting and etc. Especially, for example, meeting with you today. Never
Yeah,
did
I've
this.
done more. We did some of these before the pandemic, but I've done way more now, and there's no way you could travel to all the
Yes.
places that want to do talks. So this has actually worked out a lot better for people.
Great.
Thank you.
Great. And something else. Now you are sitting in Florida. You are enjoying the hot weather there, and we are sitting in Jordan. We are enjoying the cold weather here.
You have cold weather right now?
Well, it's not that hot. You know, it's around 30 degrees C, which is how much? 70 something degrees Fahrenheit, or around 80s, right, Yahya?
You know, it's probably
yeah,
not so far
75
off.
actually.
It's in the 80 degrees.
Oh,
here
great.
daytime, so it's not too bad.
It's around 75 here.
75 here. Okay.
Yep.
That is more
All right.
and dry.
At night, it's getting very cold.
Yep. Dr. Kiwan and Ms. NUJOUD, we are live now on YouTube. And then we can start because I know NUJOUD has to leave to the airport in 1 hour from now. So let's get to the presentation. But before we go to the presentation, first of all, thank you so much, Ms. NUJOUD, for being with us. On behalf of APL Technologies and Jordan University of Science and Technology, we wish to extend our warm welcome and thank you to our guests of honor for this evening lecture, Ms. NUJOUD Merancy, the Chief Exploration Mission Planning Office at NASA. We really appreciate her time and effort to make this presentation come true. And I would like to welcome all our audience with us tonight to hear this great lecture that is titled as Space Exploration Praxis. But let me introduce our guest of honor to you. Ms. Merancy is a system engineer with extensive background in human space flight and spacecraft at NASA Johnson Space Center. She is currently the chief of the Exploration Mission Planning Office, responsible for the team of engineers and analysts design, developing, and integrating NASA human spaceflight portfolio beyond low Earth orbit. These missions include planning for the Orion Multi-Purpose Crew Vehicle, Space Launch System, Exploration Ground Systems, Gateway, and Human Landing System. She's also responsible for ensuring the mission design, trajectory, and objectives can be successfully be met by the programs and vehicles for successful human spaceflight operations. She has previously served as the Exploration Mission Analyst Lead and led the team developing the Orion Integrated Mission Execution, Vehicle Performance Analysis, and Exploration Mission Design. Her work experience includes systems integration, test and verification, vehicle performance analysis, guidance, navigation, and control, requirement engineering, and real-time operations spanning both the International Space Station program from 2002 to 2008. This Orion program from 2009 until 2018, Exploration Systems Division from 2018 to 2019, and now the Division Chief within the Exploration, Integration, and Science Directorate. Thank you so much, Ms. NUJOUD, Ms. Merancy, for being with us tonight, and wish all the best for you and your career. Dr. Suhail, would you like to add some few words?
Well, thank you, Yahya, for organizing this meeting. Thank you, NUJOUD, for accepting our invitation. Actually, this is very impressive CV for a young engineer.
Not that young anymore. So.
This is very impressive. Would like to hear what you what you prepared for us today. And since you are leaving to the airport soon, so I will say nothing more than what Dr. Yahya said, and the floor is yours, please.
All right, well, thank you for having me. I'm happy to be here. I'm going to give a talk. So the talk will be in two parts. First, talking a little bit about my current job, what we're doing for Artemis, returning to the moon, and then a little bit about the lessons I've learned from space mission design and how it applies to your career and life and things like that. So let me get the charts presented.
I think you're muted, NUJOUD. Mr. NUJOUD, I think you are muted, right?
All right, can you hear me now? I took my audio away when I went to share.
Oh, yes, yes, perfect.
All right, I'm not sure the audio on the video will play now. All right, can you see the charts and hear me?
Crystal clear.
Okay. So I just wanted to, talk about Praxis is the practice of implementing theories and art and science and skills. So that's the title here. So I wanted to start with, this is a view of Amman, where you all are at from the Landsat satellite. So just some of the interesting things that can happen. So you're there. But I grew up here in Washington State, which is the Seattle area in the northwest part of the United States. But my father is from Nazareth, which is, also very close to you. So I wanted to put that little picture in there. I got a degree in aerospace engineering from the University of Washington, right here in Seattle. And after I finished my degree, I went to work actually for Boeing on the space station in Houston. And here's Houston. So we're on the Gulf Coast. Normally I would be there, but currently I'm on the Space Coast in Florida. But right here at the Johnson Space Center is where a large part of the human spaceflight portfolio for NASA is managed. And while I was working, I also got a master's in systems engineering from the University of Houston Clear Lake, which is literally across the street from NASA. So it was very, very convenient. So that's a little bit about where we are and how I got there. But in terms of my job, right now we're working on the Artemis missions and the Artemis program. So we all know about Apollo having sent crews to the moon in the 1960s, early 1970s. But Artemis is the twin sister of Apollo, which is where the program gets its name, because now we'll be returning to the moon with astronauts and a very diverse astronaut corps this time, which will include women and people of color. So the horizon goal here is, as we return to the moon and actually go to the south pole of the moon, we're pressing the bounds of technology and capability such that we can eventually get to Mars. And when we talk about the south pole, so this is the south pole of the moon. And at the south pole, the sun is very oblique, which means it's low on the horizon. And as it passes through the lunar month, you can see the sun rotates around. But the important thing here is that some of these craters, this is Shackleton crater right in the middle, never see daylight. So one of the really important things about going back to the South Pole is the potential science. We might be able to find water ice in these permanently shadowed regions. They are very, very cold, so things might exist there that don't exist elsewhere on the moon, which go through extreme hot and cold cycles where you're at the equator, for example. So the reason we're headed to the South Pole is the greater potential for science return than the prior Apollo missions, which were all in the equatorial region on the near face of the moon. And when we talk about going to the moon, this is where especially my team comes in, which derives from the challenge of the mission. So if you set the goal of going to the south pole of the moon, you start to backwards calculate all of the things you need on your vehicle, on the mission design, the things you need to support the crew. So in low Earth orbit, where the space station is, it's only about 250 miles above the surface. That's 350-ish kilometers. You're only about 3 hours away from home. So if there's ever an emergency on the space station, if someone has a medical emergency, they can get in the capsule and actually be back on Earth within hours. And so that means you don't have to have such extreme measures to protect them. If someone had a medical emergency, you just bring them home. There are some supplies up there, but you would be able to get them into a hospital relatively quickly. And at that altitude, you're going 17,000 miles per hour when it returns, which leads to about 3,000 degrees Fahrenheit. I know these are all English units, which don't really help here. But when we start talking about going to the moon, you're a minimum of 3 days away. And in large part on our designs, you're more like 5 to 12 days from home, because if you're on the surface, you have to get back to orbit, and then you have to be in the right place to come back to Earth. So you're talking about an order of magnitude longer return times. So now when we take crews to the moon, you have to be able to take with them the supplies they need to handle a lot more emergencies. They need to be a lot more self-reliant, and all of those things are even harder to get there because it's so much further away. But when we also come back from the moon, the vehicles are going almost 25,000 miles per hour, and the heating is exponential. So it doesn't look like a huge change in speed, but it almost doubles the temperatures on the heat shields. So this is why things like the space shuttle are possible in Earth orbit, but coming back from the moon, we lean on the capsule shapes where you can withstand a lot more heating. And all of this, as we talk about leading to Mars, it's because if the moon is an order of magnitude harder than Earth, Mars is even another order of magnitude harder than the moon. Because when we go to Mars, it's a 2-year mission or more. It takes 9 months to get to Mars and 9 months to come home, and there's no early returns. You can't bail out on that trip. So even though it's a 9-month return, your actual total mission is 2 years long, and the crew needs to be able to have everything they need for that 2-year mission with them. And if you try to perform a direct return from Mars, you're up to over 6,000 degrees Fahrenheit. So you can see, as we start exploring on the moon, we're driving more technologies in, which is a stepping stone to Mars. So all of these things get harder. When you start talking about reliability of vehicles, they need to be safe. They need to have repairable parts or whatever you need, because the crew needs to be much more self-sufficient the further we go from Earth. In terms of our vehicle, so this is one of the programs I worked on specifically. The Orion Multi-Purpose Crew Vehicle is that vehicle where we safely launch and return the crew to lunar orbit in the Orion vehicle. So it consists of some major components. The crew module, where we can have 4 crew for up to 3 weeks. They have all the supplies they need for 3 weeks. And the vehicle itself can fly for longer, but if you want longer flights, you need to augment with additional oxygen and water, which we'll get to. The service module, which is a major component, including the barrel section you see, the solar arrays, the radiators, and all the tanks, are provided by the European Space Agency. So we're actually already an international program on Artemis, with more to come. And then the last major element is the launch abort system. That actually is only used, so to speak, for the first 2 minutes of launch. After we get up high enough on the SLS rocket and the solid rocket boosters jettison, the launch abort tower comes off. It's only truly used in an emergency with the rocket to pull the crew capsule free and bring the crew safely home if needed. So this is the major parts of Orion. Like I said, this is 4 people for up to 3 weeks. So it is quite a camping trip with your 3 best friends in here. The Space Launch System is the rocket we've been working on. All of this is literally being assembled here at Kennedy Space Center right now. The one in the middle is the Block 1 version, which is what we're going to launch on Artemis 1. So you can see Orion at the top. And then the rest of this is the Space Launch System rocket. So this is used to get Orion to low Earth orbit. And then the upper stage, which is buried here under the American flag, that is the translunar injection. So that's the stage that pushes Orion out to the moon. So the whole mission for the Space Launch System rocket lasts about 3 hours, and then it's used up, and then Orion performs the rest of the mission. But when we're talking scale, and that's one of the amazing things seeing it, is it's big. It is very, very big. So the Saturn V here is shown for reference, used for the Apollo missions. Our Block 1 rocket is a little bit shorter, but we're actually upgrading that upper stage to be more capable on later flights. And it'll get 1 foot taller than Saturn V when we're done. It's actually limited by the height of the assembly building because you need to put all these pieces together. So that assembly building was built for the Saturn V. So that's why you end up with a similar height for our SLS Orion Block 2 vehicle. And just in case you didn't notice for reference, this is the scale of a person and a giraffe next to these vehicles. So when we talk about how big they are truly very, very large vehicles that we're launching. And here we are. This is actually where I am. This is part of the view I have right now, which is the Kennedy Space Center, where Exploration Ground Systems will serve as our launch vehicle. So you can see here is the mobile launch tower. So once all assembled, the Space Launch System rocket and Orion are on that mobile launching platform. The crawler, which you can't see, it's underneath here, rolls it out to the pad. We have a very clean pad in this configuration, and then SLS and Orion will launch. One of the other pieces for our ground systems team is they perform recovery of the crew. So when the mission is done, Orion will land in the Pacific Ocean near the California coast of San Diego. And our Navy, we partner with the United States Navy, and they use a well-deck ship to recover the vehicle and the crew. So all of this has to be coordinated, and this is where mission design comes in. We'll play this video.
2, 1, 0.
I'm going to pause it and make sure the audio is playing for you. So I have to reshare.
The audio is good. Perfect. We can hear.
The audio is good?
Yep.
Okay. All right.
2, 1, 0. Liftoff.
Artemis 1 will lift off from Launch Pad 39B at NASA's Kennedy Space Center in Florida. 8.8 million.
Did the audio stop?
No, the audio is fine, but we can see the presentation.
Oh, I did take off sharing.
Thank you.
Three, 2, 1, 0. Ignition. Liftoff.
Artemis 1 will lift off from Launch Pad 39B at NASA's Kennedy Space Center in Florida with 8.8 million pounds of thrust provided by the most powerful rocket in the world, our Space Launch System rocket, or SLS. The uncrewed flight will be the first integrated test of SLS, our new Orion spacecraft, and exploration ground systems at Kennedy. Artemis 1 will send Orion beyond the moon, 280,000 miles from Earth, farther than any human spacecraft has ever flown.
This is not NASA doing this. This is the United States of America doing this program, the Artemis program, and there are companies all across our country that have a part in it. So there is kind of this wave of excitement being generated just by saying, we're going back to the moon.
After the upper stage of the rocket separates from Orion, the upper stage will deploy small satellites over several days to perform science experiments and technology demonstrations. Orion will make its multi-day outbound trip to the moon, propelled by a service module provided by the European Space Agency. Engineers will test Orion's systems on the way to the moon. Then, Orion will fly about 60 miles above the lunar surface, using the moon's gravity and engines on the service module to enter a lunar orbit. After about a month and a total distance of over 1 million miles, Orion will return home, faster and hotter than any spacecraft has before. A primary goal of Artemis 1, ensure Orion safely returns to Earth before we fly with humans. When we do, we'll build our capability for sustainable lunar exploration, preparing us for missions farther into the solar system.
Initially, what we'd like to do is start establishing a presence on the moon. So we're going to establish going back there on a regular basis, and then we'll end up setting up Gateway, and we would launch to the Gateway, and from Gateway, land on the surface of the moon.
We are there for, weeks, months on end. And there, we're going to be able to test out all the hardware and the habitats and the hatches and the suits and the rovers that'll allow us to prove out those technologies. The moon will lead the way to Mars, and we should be there within the next couple of decades.
You are muted, Ms. Merancy. Muted. You are muted.
Okay. Video keeps muting me.
Yes.
All right, so as mentioned in the video, the Artemis 1 mission is what we're working on right now. We're actually, the teams are working very hard to try and launch by the end of this year. So when we're talking about doing this, this is very much a real thing we're doing today. But the mission design is what my team specifically works on. So for Artemis 1, it is putting all those pieces together, the Space Launch System rocket, Orion, working out the trajectories. We'll be entering a distant retrograde orbit, which is a very large orbit around the moon. It is called retrograde because it's the opposite direction of the moon's rotation. So in this picture, the moon would move to the right and Orion moves to the left around this orbit as it's circling the Earth. So a lot of stuff going on here, and that's really what mission design is how do we put this all together? One of the major objectives of this flight is that flight test of the rocket, the Orion spacecraft, the ground systems, because this has no crew on it, but on Artemis 2, we will fly crew. So this is our final essentially system verification test of everything, including that heat shield reentry into the atmosphere. We can't fully duplicate the conditions of entry in labs on Earth. So this is the final test of the heat shield, for example. So all of these things are being done before we put people on board for that reason. So in terms of mission design, it's a very complicated, you have to work with all the teams. So I just wanted to take a moment and step back and over my years in my career, learning some of these things and how they apply to the choices I've made. The Wheeler principle is essentially to never make a calculation unless you know the answer. And that seems counterintuitive, but shown here is the Apollo mission profile. So this is the map of the Apollo missions in a graphical form. And the point here is that if you're going to the moon, you have to guess at the endpoint and then you work backwards through the steps of how to get there. So you start with the end in mind and then make a plan. And so the same thing here. I actually wanted to be an astronaut when I was young. So if the goal is to be an astronaut, well, then what do I need? I need the aerospace degree. I need experience, things like that. I won't be an astronaut, but I did make the plan with the goal in mind and still ended up where I am today. So you always have to set the goal and then work the plan backwards from there. And that's the Wheeler principle. And then my first job out of college, as mentioned, was on the space station. And Aikens' first law says engineering is done with numbers. Analysis without numbers is only an opinion. And this is probably a great introduction to engineering when I started working on the space station, because I supported real-time operations. And the first thing you learn is never state an opinion. If you don't know the answer, you say you don't know the answer. So learning to back out and not try to have pride first, right? If you don't know the answer, you say so. You do the work, you work through the analysis, and only then do you bring the answer. So if you don't have it, you don't bring opinions, you bring answers. So this is the first thing you do when you're learning to establish technical credibility, is you actually say when you don't know something, and then you go work it out. So that is a very important rule to learn in your career. And then lastly, delta velocity. So this is the change you need to get the acceleration you need to get from one point in space to another. And the interesting thing about this is there's no shortcuts. It doesn't matter what orbits you use, what rockets you use, whatever. If you leave the Earth's surface and you want to go to the moon, you have to produce the energy needed to get there. You have to put the work in. So there's no way to, people are talking about different companies and the rockets they come up with, but ultimately everyone has to supply the energy needed to get to the moon, and you have to put in the work along the way. So this is one of those things where, you have to put your head down, keep working, you set the plan, at what you started with, and you work through it until you achieve your goals. And there's no shortcuts in your career, in life, or in mission design. And then one of the most important things, so Shay's law, is the ability to improve a design occurs primarily at the interfaces. This is also the prime location for screwing it up. So we saw in that video, we saw the Gateway program. And so here's an image, a rendering of our plans for Gateway. You can see Orion on the end, a human lander system on the bottom, and Gateway in the middle. The problem, not the problem, the opportunity, so to speak, is all of these things are very complex. So when you've got one program working with another program, the most likely place that they will have an issue is at that interface. Someone makes an assumption about what someone else is doing, what the other vehicle will do, etc. So this is why communication is so important, and teamwork in what you're doing. It's true about the vehicles. It's true about the engineering teams themselves. You have to be able to communicate and listen to the other teams around you, because that interface between teams is the most likely place that you'll have an issue in the design. And that's whether you're on the same program between subsystems, between different vehicles. Communication is the underpinning of everything we do, and learning to very well explain what you're doing to others, listen to what they're saying, is one of the most important things in a successful space mission. And one of the, in the trajectory world, this is one of the most important factors. So the Oberth Effect, the most effective time to make a change is when you're moving your fastest. And so that's where it's counterintuitive in some cases. But when we fly by the moon and we're using the moon's gravity as that slingshot, that is when we actually turn the engines on for Orion or for any space vehicle. You do it at that moment that you're passing by the moon at the fastest point, because when you insert even the tiniest correction there, it makes the biggest impact. And the same is true for your careers, that when you are, working through problems, you've been on a program for a long time, you're actually excelling at what you're doing, that is actually usually the time to make a change, because you need to learn something, you need to, find something new to do, you need to find a new way to help the program. So counterintuitively, you always actually take the biggest risk when you're doing your best and you're moving your fastest. By making the small change there, you have the largest impact. So you always need to be cognizant of what's going on in your career and what's happening around you, and look for the right opportunities, that right moment to make a change. You don't fire the engines all along the way. You're wasting your propellant. You always time it to make the smallest impact at the biggest period of time. And control authority, so this is very simple, right? The capability of the flight controls to control the vehicle. And that's truly, we can only control what is in our sphere. So you need to learn to trust those around you, influence and manage up, right? I have the ability to control my work, my effort, and get it done. In this case, there's a lot of times where you can see a problem and you need to find ways to influence those around you to make a change. There was one time, we didn't have sufficient communication antennas around Orion. There was a big hole in the comm coverage, if you will. We wouldn't have had line of sight to the satellites. It was a big impact to the program, but I actually put together all of the rationale for why we needed to do it. The mission design was necessary, supported it, and worked it through the program managers to get it done. So you have to use that influence and your sphere of control. And through the analysis of mission design, we led to a major change on Orion to support the mission that was there. So always work through with the data, the analysis at hand, to influence those around you and fly the vehicle. The vehicle is flown from the back end. It's not flown by the managers on the top. It's everyone on the bottom is controlling the vehicle through their hard work to get it where it needs to go. And this is sort of an American idiom, but it is very applicable, and it actually originated in the aerospace industry. Murphy's Law: if there are two or more ways to do something and one of those will result in catastrophe, someone will do it. This actually originated in the 1940s. There was a rocket sled incident. Things were done wrong. And generally, this is all procedural error. Those types of things that, it was a small mistake can lead to large catastrophes. And the picture here is actually the Genesis spacecraft. So this spacecraft went out and sampled a comet. So the dust trail behind a comet, It used big panels to collect samples from that dust trail. The mission was a huge success. And then upon entering the Earth's atmosphere, the parachutes never deployed. So it literally crashed. This is the Utah desert. You can see the helicopters and the recovery in the background. And the reason it crashed is because one accelerometer, a sensor that detects what should have detected when it was slowing down in the atmosphere, was installed backwards. So the whole mission came down to one accelerometer being installed backwards because it wasn't dummy proof, essentially, right? It had no markings for which way went which way. So it went in backwards, and it all came down to that one accelerometer backwards. So that's where, making sure that you work through the process, always check your work, make sure things are foolproof, because no matter what, you have to check the small things, otherwise you avoid catastrophe. And the last thing I wanted to point out, right, is Aikens' third law, which is that design is an iterative process. And it's always one more iteration than you've completed is necessary. And the lesson here is really that you always need to drive change. You always need to be learning. You always need to be growing. And so while my career, it has a lot in it, right? I started on the space station, and then I went to Orion, and now I'm doing mission design. The point is that I'm always learning something along the way. When you first start a career or a job, you should be overwhelmed because you shouldn't know what you're doing. You should be learning on the job. And as you learn on the job, you should be improving it, and then you should be teaching someone else, and then you should be finding a new challenge. So it's always an iterative process that your career is a series of growth. You should be looking for challenges every single time you change jobs, every single role you're in. If you're not learning something, then you're standing still. So always be learning something. Your mission design is an iterative process. We start out guessing the answer, and we get better along the way. So if you started with going to the moon, and now we leave the Earth, but then our rocket didn't quite have the performance it needed or something, we changed the trajectory. So you always get smarter on every single step. Your career and the mission designs work the same way. We always iterate on the design to make it better along the way. So in summary, and then we'll do questions, these are sort of the lessons learned from mission design. We can apply them to our own careers. This is how I've applied a lot of things to my career. You have to make a plan. You have to do the work. You find your path. Everyone's path is different. Communicate. And you take the risk on change. You lead from below and influencing what you have control over. You have to be resilient to the setbacks and make sure you're checking your work like the Genesis program did. And then you're always learning and iterating. And this last slide I wanted to pause here, right, this is Mars. So this is a sunset on Mars. We have red sunsets on Earth. The sunsets on Mars are blue, just the difference in light scattering in the atmosphere there. And that tiny little dot in the distance in Earth. So everyone we've ever known is on that little speck of a star, essentially, in the Martian sky. And all that we're doing, as I mentioned, this going back to the moon, working on these vehicles, is essentially iterating and learning so we can get to Mars. So everything we've learned along the way is how we're going to eventually get to Mars. And so I'll leave with this picture, and we can jump to questions.
Well, thank you so much. It's a great presentation. But I have a rain of questions here. I'm not sure where to start from. Well, good. We have at least 15 minutes or half an hour to cover them. My first question is, have you thought of inflatable habitat technology in designing or adding to Orion?
Yes, so inflatable technologies are actually something NASA has been working sort of in the research arm of looking at future modules and stuff. There are a couple companies in the US, and I think there's at least one or two elsewhere around the world working on this kind of technology, because as you go out to the moon, as we go to Mars and you spend longer and longer in space, you need all that stuff. Like you need food for 2 years, you need, equipment to fix any systems that fail. So an inflatable module, the real advantage of it is you can pack it into the fairing of the rocket, but then make it much, much bigger on orbit. So yeah, these are something that NASA has been looking at. There's a large potential that we might put one on the Gateway in the future. It's just not committed yet because it's still in the research phase. But these are the types of modules that would be very advantageous for a Mars mission. So yes.
Okay. Well, thank you. How do you guarantee the spaceship safety when orbiting against space debris?
Space debris is a huge problem, yes, in low Earth orbit. Especially, it's about 500 miles, 600 miles up to about 1,000 miles. There's actually a large belt of debris that's been generated from satellite breakups and various things over the years. The space station flies just below the worst of the debris, so it generally stays safe, but there's actually a lot of panels, ballistic panels on the front of the vehicle that can take a significant number of impacts to them and break up the orbital debris that hits it. So you can only handle up to a certain size, right? And whenever there's something big, we can track that with radar on the ground, and the space station will actually move its orbit to avoid it. So there's a mixture of small stuff you can, attenuate with ballistic panels. Large stuff you actually move. A lot of our Artemis 1 mission, a lot of the risk is actually in the Earth orbit before we depart for the moon, because we're flying through those debris fields. So as you fly out to the moon, you have to cross the debris field. When you come back, you're actually going really fast, 25,000 miles per hour, and you're slicing right through that debris field. So there is a significant risk, but we also can't do anything about it, right? There's some amount of risk that we have to accept on any mission, and it's always judging what the right level of risk is. As we go out to the moon, there's not a lot of debris in orbit there. There are micrometeoroids. The challenge there is we don't have the ability to track anything. So as more and more stuff goes to the moon, this will probably become a problem over time, because you don't have radar systems like we do on Earth to track other satellites and things like that. So there's a big challenge out in front of not just the US, but all of the world for anything that goes out to the moon, keeping track of where everything else is to avoid it. Yeah, micrometeoroid and orbital debris is a big issue on space mission design.
All right. Well, this is a technical question, I guess one from our students. How many kilograms or pounds of thrust for proposed Orion to have, and how do you maintain a spaceship orbiting around the planet? I guess you mentioned that. You answered that question.
So, I mean, I don't know the numbers offhand. I think the video was like 8.8 million pounds of thrust on the rocket.
I remember.
And Orion, much smaller. The bigger the vehicle, the bigger the thrust you need. Orion is actually reusing one of the shuttle OMS engines, orbital maneuvering system engines. I can't remember the thrust on it. It has like a 310-second ISP for anyone that knows rocket engines. And there's 18,000 pounds, 8,600 kilograms of propellant on board Orion in the service module. And that's enough to perform the whole mission, getting out to the near rectilinear halo orbit and home again. So a lot of stuff, goes into it. The Space Launch System rocket is actually reusing the shuttle main engines. And now we're building out more. They're called RS-25 engines. So there's a lot of reuse of hardware and engines, but then we're building the production lines for later flights.
Yeah. Why NASA decided to go back to the moon, and what exactly this will offer us as a humankind on Earth? And I think this is 3 questions. And the third one, are you planning to have rovers on moon and lift it there and leave it there?
Yeah, so this is great. So going back to the moon, there's sort of 3 reasons. I like all of them. I don't think we have to pick. One is the science. Only 6 people have walked on the moon. The moon is the size of the continent of Africa. And so if you said we'd put 6 people on all of Africa, therefore had been explored, I think that's wildly underestimating the science return, the potential things we could learn. So I think there's way more moon to explore. It hasn't really been done. So that's one reason. The second reason is, and the third really both together, is the technological gain and the economic gain. So the point of doing this is that if you set hard challenges, you develop the technology to support it. No one would necessarily invest in the solar array technologies we use today if space systems weren't leading the way in the past. things like the global positioning system, the things we take for granted now, satellite television, right? That was all like spurned by the Apollo program and that push into space in the 60s. The same thing can happen here. A lot of the technologies we need for these deep space missions could have benefits on Earth, like regenerative life support systems, being able to reclaim water. All of those are technologies we drive into. The space station has a whole water reclamation system. It's over 90% efficient. So all of the sweat and the urine the astronauts produce, it goes into the system and it produces crystal clear water at 90% efficiency. I actually learned just the other day that when we go to Mars, we need to achieve 98% efficiency. So those types of things are the drivers for technology, and there have benefits here on Earth. I mean, Jordan is a desert climate. If you could use water reclamation, cleaning systems the same way we are on the space station, there could be a huge benefit to the infrastructure here on Earth. So, and then that just drives the economies. It promotes jobs and things like that. So there's a lot of reasons to do exploration. All that money gets spent here on Earth. We don't burn it in space. There's a lot of good reasons to do space exploration. So there's three. What was the other question was rovers on the moon. Yes, absolutely. We're actually very close to putting out in government speak a request for proposals with industry on who wants to build us a rover. We intend to, on Artemis 3, return to the surface of the moon. And just like Apollo, by Artemis 4 or 5, we want to have a rover for them to be able to get around so that way they can do more science and reach areas further from wherever their landing spot is. So yes, and this is part of our goal, is the sustainable exploration plan, right? Apollo spent a huge amount of money to go very fast, but that made it not affordable to continue, which was why it got canceled. We're working on very fixed budgets and building things incrementally. So we start with the rocket and Orion, and then Gateway and a lander, and eventually we want to be able to put habitats on the surface of the moon and to go for longer and longer exploration missions and be able to continue this over many decades and not simply do 6 missions and quit.
All right, thank you. Hello, Ms. Merancy, I have a question. How the astronauts are training for life in space? Have you tried to be in their environment before? And also, what is the longest days you can stay on the space station?
Oh, good question. So the astronauts, right, and NASA has a lot of experience training crews for space. They do a variety of things, whether it's, you know, literal classroom lessons. It always builds on the stuff. You sort of start in a classroom, then they might do VR, virtual reality type training. And there's a lot of field testing for them because especially for the astronauts, they need to be able to respond in high pressure situations. So that's why they fly jets, to get their skills up, to be able to react quickly. They go out in the desert, they go on survival training in, you know, the tundra of Russia. There's lots of different things they do because they need to be able to basically be calm in an emergency. So a lot of their training is not just on the systems on the space station, it's training them to be very good in emergencies, to work as a team, because they're confined space. You've got to be very good working with those team members. You can't walk away from them. I have tried to be an astronaut, but so have 18,000 other people every time applications come out. So I have not been successful, but I have gotten to fly on what was the Comet, the zero-G aircraft. So I have gotten to experience weightlessness on the aircraft during the parabolas it makes. So that was cool. So I have gotten to do a few things, but not like the astronauts get trained for. In terms of durations, generally it's about 6 months for the crews on the space station, but it has gone as long as a year. And on Mir, the Russian space station in the 90s, they had some folks fly for even longer than that. So we're getting very good at keeping the crew healthy for 6 months to a year in space. Going to the moon, we're going to likely be looking at more like month-long missions, 2-month-long missions. But like we said, when we go to Mars, we need to get up to 2 years. So being able to keep the crew safe for 2 years in microgravity and be able to do physical things when they land on the surface of Mars, those are a lot of the research areas going on because it's even bigger challenges than we're prepared for today.
Yep. I like your comment when you said that don't answer from or don't convey your opinion. Just give me your solid answer about or that is based on analysis and based on a numerical simulation or numerical calculations. And I like that because it's really important for our students and our audience who with us tonight to really, when it comes to a very sensitive issue, just like space or designing even trivial things, just base their opinions based on evidences rather than just opinions. I like that. What makes your job interesting, Ms. Merancy? Why
My
you like
job,
your job?
I like my job because I'm a big picture person. I like seeing the whole puzzle and figuring it out. So, you know, some people like to become experts on one thing. That's what gets them jazzed, that they, you know, they know, say, aeroscience better than anyone else. They know how the aerodynamics works. I like seeing the big picture. So, you know, I'm a mile wide and an inch deep in everything. So I have to learn a little bit about everything. We have to solve the puzzle. It is a lot of working with the teams, right? Because I'm not the expert in anything, I'm sort of the expert in putting it all together. We have to learn a little bit about all the vehicles, find the different solutions, and then trade them. Everything we do is a trade, whether it's for cost, schedule, risk, the technical feasibility, the benefits of the mission. You can't optimize for everything. So we always are trading, you know, this is what's best for, you know, the rocket, and this is what's best for Orion. So it's the figuring out a solution. That's why I like my job.
All right, perfect. I have a question that you might can help me to understand. Is there a specific time that you are not allowed to surpass when you are in space?
A specific time? So no, not really. A lot of it is based on, you know, planning for keeping the crew healthy. So in a lot of cases, the limits are first the physiological factors, the muscle and bone density and stuff. And that's where our flight doctors and stuff have gotten very good at the exercise protocols. And some of the astronauts come home stronger than when they left. You can do a lot of that for muscle strength, but bone density tends to degrade. The radiation is the other big limiter. So there's no one knows how much radiation is too much for any individual person, right? We have limits on the radiation dosage for the crews because they're not on Earth. They're not protected by the atmosphere as much. So they get quite a bit of radiation on the space station. 6 months radiation on the space station is about 2 weeks of going to the moon, because you have to pass through the Van Allen belts going to the moon. So the radiation is one of the biggest limiters, and which is really a risk for cancer. And you can't really like predict exactly how much of that will lead to cancer or not. So there's limits on how much radiation exposure the crew can take. That's another one of those things that if they go to Mars for 2 years, the finding ways to protect the crew from radiation is actually also one of the biggest challenges. So I've talked a lot about the challenges of going to Mars are less technical and more centered on the human physiology. Humans were not meant to be in space, and space finds many different ways to kill you. So trying to keep the crew safe for a 2-year mission to Mars is one of the biggest challenges and the biggest roadblocks to actually putting those missions together.
Do you see that happening in 10 years to the moon or to the Mars?
To the moon, absolutely within 10 years. We're flying Artemis 1. The vehicle will be tested out around the moon. I fully expect we'll be on the surface of the moon within the next, 5 to 6 years, not even longer than that. Going to Mars, I think you're looking at least the 2030s. There's just so much stuff that you need to get to Mars. There's many, many, many hundreds of metric tons worth of material between the rockets, the food, the solar arrays, all the propulsion. There's just a lot of stuff needed to go to Mars. So in order to build that up, that's going to take time. So no earlier than the 2030s for a Mars mission.
I see. Yeah, this is a good question. How do these vehicles obtain energy when flying in space?
So they obtain energy. So this is actually green technology. So first, propellant is all taken off the surface of the Earth. So one of the major forms of energy is the translational thrust needed to make the mission work. We take that all in tanks from the ground. In the future, we might be able to generate, it's called in situ resource utilization. If we find water ice on the moon, water is made of oxygen and hydrogen. that is rocket fuel. So if you can find ways to mine water and split it into tanks of oxygen and hydrogen, you might be able to find energy that way. But the other major systems are run off of solar power. So all of our vehicles use solar arrays, and we turn free sun energy into electrical energy to run the lights and the computers and all of those things. So most of our systems are solar array powered. Because we're going for months at a time, we're going for long durations. Apollo used fuel cells. So it hydrolyzed the fuel on board to create electricity out of, but that means you have limited to the tanks you brought with you of whatever fuel source and your fuel cells are. So that's why all of our vehicles today use solar arrays, because you want to be able to go for long durations.
Yeah, I see. Well, it's a lot of calculations for the fuel and what kind of fuel that you use in the vehicle as well.
Yeah, these are all trades. Like this is in the vehicle design, right? You figure out what you want to do, and then you work backwards. You know, we want a long mission. Okay, well, that's probably going to lead us to solar arrays instead of fuel cells. You have to work through the system design of what you need to accomplish the mission.
I see. What are the, I think we all dream to be astronauts one day. What are the qualifications needed for traveling in space? And do you see it is possible for specialized or for not specialized individuals to join the near or in the near future?
So, I mean, I think that there's sort of a revolution going on in space travel, right? So for NASA astronauts, you need a master's degree in an engineering or technology field. So engineering, math, doctorate, science, like doctors and stuff, and at least 3 years work experience and good physical health. It's not actually a lot of requirements, but they get such highly qualified candidates. You'd think there were more, because these people are all pretty phenomenal in what they've accomplished. But that's to be a professional astronaut, so to speak. Now, you know, if you've been watching the news, Blue Origin and Virgin Galactic both recently had flights for basically tourists, suborbital. There's one coming up with SpaceX called Inspiration 4, where they're actually sending 4 people into orbit. They're not coming to the space station. They're just going to do a few-day mission in orbit. It's all a privately funded venture. So for those folks, it's sort of, you know, generally good health is what the requirement is for them, right? And a lot of money. That's the hard part. I'd love to go to space myself, but I don't make that kind of money for the costs of these flights. But I think what we're seeing is just like early air travel, this is the early stages of space flight for non-professional astronauts. So hopefully in the next few decades, this will become much more accessible to us normal people, if you will.
Oh, I hope so. Well, I don't have that kind of money as well, so I'm okay with being here. So what is the nature of terrain on the moon, and what is the difference between the air soil, Mars soil, and moon soil?
Good question. So the terrain on the moon, if you're on the near face of the moon, it's mostly flat plains and some hills. So you can, when you look at the moon in the night sky, you can see lots of very flat areas. On the South Pole, there's a lot of craters and ridges because it hasn't been impacted more with asteroids over the years. The near side, you know, is sort of protected, so it's not nearly as hilly and mountainous. The South Pole and the far side are very rough terrain. And especially on the South Pole, where you have those craters that never see the sun, all of our landings and where we put habitats and things like that will be on those ridges around the craters, because we need them to be in sunlight to create energy for the crew, to have temperatures that are acceptable to having a vehicle sitting in, right? We can't land a vehicle in one of those shadowed regions because it's a couple hundred degrees below zero. So it's very much ridges and craters. And we'll be looking to be on the ridges around craters to keep the crew in sunlight while they're there. So just think, you know, if there's a big canyon like the Grand Canyon in the US, there's a lot of that type of terrain. The soil on the moon is mostly, it's called regolith. It's a very, very fine powder. It gets into everything. It's actually one of the big technical challenges is how do you keep that fine powder of regolith from getting into the joints on the spacesuits, things like that. You know, they're going to come inside their habitat and it sticks to their spacesuit, and now your habitat is filthy. How do you deal with the lunar dust is a big challenge because it's sort of got an electrostatic charge and it sticks to everything. So there's a huge challenge of lunar dust that it's not quite like on Earth. But if you think about dust getting into like the joints of a mechanical equipment, it's the same problem on Earth in that regard.
I see. Is it the same as Mars?
So Mars is probably closer to Earth in that regard, different chemical compositions, stuff like that. But I mean, I think it's generally closer to Earth. We have samples of Mars dirt that, you know, people do testing on and stuff like that, but it is more like a desert environment on Mars.
I see. This is a good question. What kind of materials are used in the housing of these vehicles in order to cope with such extremely high temperatures?
Good question. So this is where technology has advanced a lot since the 1960s. Orion is the same shape as Apollo, the same degree backshell angle and everything, because the physics of the aerodynamics hasn't changed, but a lot of the material technology has changed. So the majority of our pressure vessels are aluminum. They're machined out very thin to be as lightweight as possible, but the pressure vessels are generally aluminum, similar to an aircraft frame. Inside, though, we use a lot of carbon composites. And a lot of the service module structure on Orion, for example, have big carbon fiber panels holding it together, and then aluminum pieces and stuff like that. So a lot of it's carbon fiber, aluminum, titanium, because it's lighter weight where we need it. So it's all about getting it as light as possible, but doing the job and being as strong as possible. So we use a lot of those technologies. They didn't have carbon fiber in the 60s. So we actually have way more room for the crew inside Orion than Apollo did, because our computers are smaller. Carbon fiber lets us have stronger structures with less material, right? So there's a lot of improvements to the vehicle, even if it looks very much the same. On the inside, you can definitely tell the difference, though, between Apollo and Orion.
True, true. I get this question. Probably you can help me understanding. Why don't you switch to using SpaceX Starship instead of the SLS? I don't know what that is.
So, you know, first off, we are using Starship. That was the vehicle that NASA selected as our human lander. So Starship is the landing system we're looking to do on the moon. I will say Starship is not qualified to launch astronauts, and nor can it be. It's not designed to be able to abort with crew on board. So you can't launch with humans on Starship. That's not in their plans for it. So one of the reasons there is, right, first off, we were already developing Orion and SLS. Starship is a more recent development, but NASA is using SpaceX's Starship as the lander system. We'll actually get confirmation of that next week, as we've only recently selected, and there's been government processes getting that in place. So yeah, we are using Starship, but it is the lunar lander.
I see. I think we have 4 minutes left. I have this interesting question. Is it possible to predict life outside our planet, and what are the basics of these predictions?
So that's a great question. So I always go back to Carl Sagan on this, that if life doesn't exist in the universe, it's an awful big waste of space. So there are billions of galaxies, billions of planets that in the known universe, just what we know that there's billions out there. So my personal opinion is that there is life somewhere, and we simply haven't found it yet. Now, why we haven't found it, I don't know. You know, there's potential for microbial life, things like that. That's one of the reasons of going to Mars, to see if we can find things like microbial life on literally the next planet over from Earth. But truly, the odds that in the billions of galaxies out there that we're all alone just doesn't strike me as reasonable. So no, we haven't found any today, but I believe it's out there.
All right. What is the proximal percentage for any vehicle to explode in space?
The approximate percentage?
What is the proximal percentage for any vehicle to explode in space?
Oh, to explode. You know, we try to avoid that at all costs.
True.
The riskiest part of the mission is actually getting to space. The highest dynamic environment is the rocket, getting to space. We manage the risk down as much as we can, but that is always the most dynamic and the highest risk on the vehicle. But that's why we have the launch abort tower, we have continuous abort coverage. So at any point in the launch profile, if there's a problem, the capsule can come off safely with the crew and they will land separate from the rocket, but you can never remove all risk. I mean, truly, if the rocket exploded and Orion didn't have time to get away, there's always a risk there. Once it gets to space, it's very risky, but you have time to deal with a lot of emergencies. But when we're talking about going to the moon, the risk for loss of crew is managed in the 1 in 100 to 1 in 200 type range, just because so many things have to happen and so many things could go wrong. So it is still very, very risky to go to the moon. And that 1 in 100, 1 in 200 means in every 100 to 200 missions, there's a chance you could lose loss of life, or loss of vehicle, which is what we're managing. So this is not easy by any means, but you try to minimize the risk and provide contingencies capabilities.
All right, this is our last question. I know it's I can't contain all the questions. There are tons of questions. And thank you so much, our audience and followers on APL, for throwing all these questions. But I apologize for not giving Ms. Merancy all your questions. But hopefully one day we can have another chat with her and be honored to have her again. This is the last question. Can we use planetary energy someday?
Use planetary energy?
Yes.
So I believe so. I mean, that's one of the advantages of like in situ resources would be to use the material at your location to generate energy. So whether that's making rocket fuel, or if it, like on Earth, we can do things like geothermal energy. That's not possible on the moon. It doesn't have a volcanic core. So there's lots of ways that we can use energy, but building the technologies to be able to do that is what's actually really important, right? If we could generate fuel on Mars from water ice that would return the crew, well, that means that's that much less stuff we have to launch and carry to Mars. So yes, there's a lot of research on in situ resource utilization, which is things like making fuel, making electricity from the available resources where you're going to. And it is very, very important that we develop those technologies.
One advice to our questions and whoever I don't want to ask you these questions, but just an advice to our flat earthers friends. What is the advice? The Earth is a sphere, right?
The Earth is round. It's a sphere. There's no way that this conspiracy theory could involve this many people. It is a very, very round planet Earth.
Good. Thank you so much, Ms. Merancy. Thank you so much for our people and followers on APL and whoever asked questions. We apologize for not getting all the questions to Ms. Merancy, and hope one day that she can have free time to be with us and have a good chat like this in the future. Ms. Merancy, thank you so much for being with us today. I would like to express my sincere thanks, as well as Dr. Sohail, sincere thanks to you for making this evening very informative and exciting. And
thanks for having me. It was a lot of fun.
I wish you the very best in your career endeavor. And thank you all for watching and being with us tonight.
All right. Thank you very much.
Thank you. Thank you so much. Have a good day.